So a student was interested in talking more about contingency tables. So a contingency table is gives the joint distribution for two discrete and actually finite random variables. So let's say I have a random variable x that can take on values in 1, 2, 3. So the probability x takes on 0 or 10 is 0. It will never take on anything but 1, 2, or 3. Likewise, y is in 1, 2, or 3. So if we wanted to completely describe the relationship between these random variables, we can give the probability that y takes on some value and x takes on some value for each combination of these values. So if we give, let's say for x taking on 1 and y taking on 3, that's a possible outcome of running a simulation. If we give that probability and we give that for each combination, we completely describe the distribution, the joint distribution over x and y. So since these are finite, we can give this in a table. So this is what a contingency table is. It completely describes the joint distribution. So y can take on 1, 2, 3. Note here that 1, 2, 3 is just a coincidence that these are the same. This could be 0, 4, 5, 10, and this could be 1, 2, 3. Or these don't have to match up, right? It's just a coincidence that these sets are identical. So 1, 2, 3. And we can give probabilities here, and the probabilities here will completely describe the relationship between x and y. So I'll start off just giving this. So the first thing to check is if we run an experiment, some outcome must result. So 1, 2 must be an outcome, might be an outcome, or 2, 1. Some outcome must result, so this is a probability distribution, right? The pairs of x and y results, the probability of any of those pairs coming out is 1. So the sum over these must be 1. So 1/3 plus 1/3 plus 1/3 plus a bunch of zeros is 1. So that checks out. So that's the first thing to check with the contingency table. Do the probability sum to 1. So the next thing we can do, we can compute lots of properties from this contingency table because this completely describes this distribution. So one thing we can compute is disregarding y, just what is the probability distribution over x. So this is called the marginal distribution, and you get this by marginalizing, which is, you can think of it as getting rid of one variable. When we have this total relationship over both of these variables, we want to get rid of one of the variables and just look at the distribution over x. So we can get this by marginalizing, so probability x equals x is the sum over all y's. Probability x equals x, y equals y. So in this case, the probability, for example, the probability x equals 1. So this probability here, probability x equals 1, is going to be the probability x equals 1, y equals 0. Y equals 1. Plus the probability x equals 1, y equals 2, plus the probability x equals 1, y equals 3. So first off, intuitively, why does this work? So y must take on some value. So the probability x takes on 1 is the sum over the probability of any of these possibilities. Because if x takes on 1, then one of these possibilities must result. So we can just sum over each of these probabilities to get the probability of this happening. That's the idea. You can prove it using lots of different methods, but we won't prove it. So if we want to compute it for this case, it would be the probability x equals 1. I'll write that here. Is going to be 0 plus 0 plus 1/3. So that's 1/3. The probability x equals 2 is going to be 0 plus 1/3 plus 0. That's 1/3. Probability x equals 3 is 1/3 plus 0 plus 0. And we can do the same for y. What is the probability y equals 1? We can compute that value by summing over all possibilities of x. Right? So 0 plus 0 plus 1/3 is going to be 1/3. So it's pretty easy for this contingency table, for this joint distribution. It's just all 1/3. So now we can check, let's say, are these identically distributed? So are x and y identically distributed? What does that mean? So for this case, since we only have a finite number of values that the random variable can take on, or that can take on with non-zero probability, we can check that the distributions are the same by looking at let's say the mass function here, right? So what is the mass function for x? The mass function for x is going to be, this is 1/3. So this is the probability, so this is the PMF, probability mass function. So this is the probability that x takes on 1. This is the probability x takes on 2 and 3. Right? So you can think of the distributions being the same, not the random variables. So the random variables are not equal. You can think of the distributions being the same as looking at so two distributions are the same if the plots are the same, right? So in this case, this is the plot for x, and this is also the plot for y. So if you look at y by itself, without looking at x, the plot's going to look like this. And if we look at x by itself without looking at y, the plot is going to look like this. Right? So these distributions are identical. So you can say they're identically distributed. But they're not equal. So what does it mean that they're identically distributed but not equal? So if they were equal, if y took on 1, then x would have to take on 1. That's not the case though, right? So if y takes on 1, x actually is going to take on 3 because it's going to take on 1 with 0 probability. So these are definitely not, x is definitely not equal to y. So x equal y, so you can think of it as like in terms of coin flips. So let's say we have 2 coins we're flipping, right? So we have a random variable for one coin. Let's call that x. We have a random variable for the other coin. This is separate from this case. Let's call that y. And 1 means heads, 0 means tails. So x taking on 1 means that one of the coin flips came up, the x coin flip came up heads, right? So we can think of the distributions are the same. Let's say these are fair coins, because if we did out the plots for these coins, you're going to have even probability of getting 0 or 1 based on heads or tails, because they're both coins that are unbiased, even probability of 0 or 1. So the distributions are going to look the same. But if one is heads, it's possible that the other could be heads or tails, right? So they're not equal. You can think of equal random variables. Equal random variables would result from the same experiment. These are 2 different experiments, identical experiments, but 2 different experiments. If x equals y, that would mean that they're coming from the same coin. So 2 equal random variables would be, let's say I flip a coin, and then on one paper I write a 1 or 0 if it came up heads or tails, and on another paper I write a 1 or 0 if it came up heads or tails. Right? So these random variables are, you could say they're equal. They're describing the exact same simulation. Right? So these are not describing the same simulation. Okay, so that's equal versus identically distributed. So now independent. Are these independent? Independent means that knowing information about one, let's say we know that y is 1, tells you nothing about the other variable. So that's the intuitive way of thinking about it. So what does this say? So let's say we know that y is 1. Well, because the probability of x taking on 1 or 2, given that y is 1, is going to be 0, we know that x must be 3. So if y takes on 1, x can't be one of these, so x has to be 3. So y actually tells you, the value of y taking on 1 tells you exactly what x must be. So these are clearly, like just first pass, these are clearly not independent. These are clearly dependent. There's a relationship between them. These are dependent, not independent. They're not independent, right? So the way we can show this is by saying, so if they were independent, then for every value that x can take on and every value that y can take on, we would have to have the probability x, y, this joint probability, decomposes as the product. So this has to, if they were independent, if they were unrelated, then you can compute any of these probabilities just by looking at the distribution over y by itself and the distribution over x by itself, and not looking at the relationship. That's the intuition behind this idea. So if they were independent, you could just look at their marginals, just their distributions by themselves, and not this related distribution, and you could exactly describe their relationship using this, right? So is this the case? So let's look at probability x equals 1, y equals 1, right? Is that a good case? Yeah, sure, why not? So this over here is 0, right? In this joint distribution, it's 0. If they were independent, this would be 1/3 times 1/3. Is this the same as 1/3 times 1/3? And this is probability x equals 1 times probability 1. So is this joint distribution of the table equal to the marginals we computed? Clearly not. 1/9 is not 0, right? So we can't describe this distribution by multiplying the two marginal distributions. So this tells us we found one case where this is not the case. So we found one case, x equals 1, y equals 1, where the joint probability is not the product of the marginals, just the distributions over each one. And so because of that, that's a counterexample saying that these variables are, there is a relationship between them, so they're not independent. So they're dependent. So proving dependence involves finding one counterexample. That's all. Proving independence requires that you're making a strong statement that there is no relationship between them. So you have to check for every single combination, so every single entry in this table, you have to check that the joint probability for that case decomposes as the product. So you have to do a lot of checks to make sure there's no relationship. To prove that there is a relationship, to prove that there's a dependency between these two, all you need to do is find one case where there's a dependency, where there's a relationship. Okay, so we have this, they're dependent. Now we can compute some moments. So moments are like single variable descriptions of the random variable. So one of those moments is the expectation. What's this? So we have the marginals for y and x. So we can compute things about these distributions. So e of x is going to be the sum x, x times p of x. Right? Just the definition. So for x, this is going to be, x, so let's say 1 times 1/3. So this is the value, and this is the probability, plus 2 times 1/3, plus 3 times 1/3. And this we get from here, 1 times 1/3, 2 times 1/3, 3 times 1/3. So this is just going to be 6/3 equals 2. So since these are identically distributed, the nice thing is we can just say that e of y equals e of x, right? I mean, if you did this, it's the same computation here, right? So if you wanted to compute e of y, it'd be 1 times 1/3, 2 times 1/3, and it'd come out to the same thing. So this is also 2, right? So let's say we want to compute the variance, which is useful for other parts of these problems that you were given. So let's say we want to compute the variance of x. Notice this is going to be equal to the variance of y, again, because these are identically distributed, right? So the variance of, let's say, so how do we compute the variance of x, let's say? So we have e of x, so we would want to compute e of x squared, and then we can combine them using a formula to get the variance. So e of x squared is going to be, let's say, 1 squared times 1/3 plus 2 squared times 1/3 plus 3 squared times 1/3. And this is going to be equal to 1 plus 4 plus 9, that's 14 divided by 3. So now if we want to compute variance of x, this is just 14 over 3 minus, so this is e of x squared minus e of, actually I'll write that. That's e of x squared minus e of x. This is a nice formula to work with. So this is 14 over 3 minus e of x squared. This is 2 squared, right? And so this is 14 over 3 minus 4, whatever. Let's actually write this out. So 3 times 4 is 12. So this is 4 2/3 minus 4. And this is equal to 2/3. So the variance is 2/3. So Other computations we might want to do. So now we have the variance over x, and we have the variance over y. And we have this expectation. So I'll write a little summary here. We do some computations. So 2/3 and 2. So far we have this chest. We have e of x equals e of y equals 2. Variance x equals variance equals 2/3. Let's say we want to get, the relationship between the two variables. So e of xy. So this together with this can give us the covariance. So let's compute this. So e of xy. This requires that we go to every single combination of x and y. So this is sum over x, y, every possible x, y. Probability x equals x. Probability y equals y. Y equals y times x, little x times little y. Right? So it's over the joint distribution is the expected value of the product. Right? So we can think of this itself as a distribution, and we can think of the value at each possibility as the product of these values. So the value here would be 1, the value here would be 2 times 1, the value here would be 3, so 6, etc. So the nice thing is this is mostly zeros. So a lot of these are going to be, it's going to be like sum, something, something, 0 times a bunch of things, plus the cases where it's not 0, where the probability is not 0, plus 1/3 times, so 1/3 times 1 times 3, so 3, plus 1/3 times 2 times 2, so 1/3 times 4, plus 1/3 times 3 times 1 times 3. And this is 10 over 3. Okay. So we have e of xy, we have the variances, we have expectations, so I think we're pretty good. So right now, we can compute the covariance. This is just e of xy. Maybe I'll go through a proof of this. So note that this here is equal to, you can just go through some algebra. This is equal to e of x minus, let's say mu x equals e of x. I'll just use shorthand here to make it like prettier. So this is what you would think of as like intuitively the covariance. This is just another formula like the one we have for variance that allows you to compute it easier. So this is for every combination of x and y, the difference from the mean of x times the difference from the mean of y times the probability. And if you add continuous variables, it's some integral just like that, similar to the summation. So here we have this, we have this, we have this, so we just plug it. So e of xy, 10 over 3, minus 2 times 2, right? So this is 3 and 1/3. 1/3 minus 4, so that's negative 2/3. So we have the covariance, and now let's say we want to compute Pearson's correlation coefficient. So when we talk about the correlation, we're usually talking about Pearson's. There are other ways of talking about it, but so let's say correlation x, y. So this is like, so the covariance tells you, if you think of this as a line, it tells you like the slope of the relationship between x and y. So here, so if we had a positive relationship, as x increased, y would increase, so it would be going like this. You have like a probability mass stretched along here. Negative means that your probability mass stretched in the opposite direction, so this makes sense, right? Negative means that as x increases, y decreases. So the slope, if you plotted x and y and like plotted scatter points and fit a line, so if we fit a line here, it'd have a negative slope, right? So the correlation is just the covariance, but you're correcting for, so this is, covariance tells you how much, it's like the slope of this line, right? And correlation corrects for the variance in x and the variance in y. So if x varied a lot, you would be dividing by that. So this is like a normalized version of how much x and y vary. So this is just covariance x, y, and you're dividing by how much x varies times how much y varies. So this is how much x and y, what the slope of the line is relating x and y divided by how wide x is and how wide y is. So sigma x, sigma y. So remember, this is sigma x squared equals sigma y squared. So the standard deviation squared is just the variance. So we have these. We have these right here, right? So remember that the variance of x equals the variance of y. So this is just covariance of x, y, divided by sigma x squared, right? Because sigma y is sigma x. So this is sigma x times sigma x squared. So sigma x squared, we have it right here. This is just, a nice result that just comes about from the fact that these are identically distributed. So we can be lazy and just use the variance without taking square roots. And so we have negative 2/3 from here divided by 2/3 from here. And this is 1. Oh, sorry, negative 1. Right? So the correlation is negative 1. It's like, it's a perfect negative 1 corrected slope line, right? So that's one case. We could go through another case, which is, let's see. Yeah, I'll come up with another case and go through that. So